So this is the model that we're going to be working with. As you can see here, I've got a floor system with a single hole. And this floor system is comprised of an area load panel that we've actually converted to a rigid diaphragm panel. So maybe we'll turn off the rendering for now, just so we can see what that looks like. Turn this off, and you can see that we are using a rigid diaphragm panel. And if I look at the span directions, I'll turn off my diaphragm nodes, I can also see that the area load span directions have been set up. And these pink lines are showing us the tributary areas for each one of our area load members, and they're also going to indicate the direction of our ribs for a particular composite floor system. So I've got my loads applied, which we'll look at in just a minute, but just to maybe explain a little bit more about what's going on here. We've set this up with simply supported beams, representing most of these joists and longitudinal beams. We do have some continuous beams here on the extreme sides in the east-west direction. I've also got some brace beams, as you can see here. And now the steel design, composite steel design that STL allows can support both simple span and continuous span beams. So that's something that you can take advantage of. You'll also see that I've got a variety of different cross sections assigned. If I just render these, you can see here perhaps a little bit more clearly. So I've got different cross sections for different elements in my model. These are my best guess cross sections. We're going to go through the process of actually designing these later on. And the model is separated into different groups. And this is going to help me with my design. It's going to help me kind of facilitate my design group setup. So I've got my girders, I've got my hole edge beams that you can see along the edge of these holes. I've got one bay that I'm going to say has restricted depth for some equipment that we want to leave room for. I have my perimeter beams that aren't already part of my brace beam folder. I got my columns, my braces, my brace beams, and then finally my joists. And so we're going to go through the process of designing these as a composite steel floor system. I also want to introduce the loads. So if I go to the loads window and I'm going to turn off my rendering here, we can see that we have 6 different load cases. So we have a self-weight load case. I also have here a slab load case, and I'll switch to my area load tool so I can see what magnitudes we're using. So you can see the magnitude of 2.15 kPa, 2.4, 4.75, 0.95, and then for our cladding load case, we have basically along these perimeter beams here, a 7.3 kilonewton per meter load applied there as well. And these are all combined together. So I do have some load combinations. If I go to the spreadsheet, it might be easiest to view this. And I click on the hand button to switch to my load spreadsheet. I can click on load combinations, and I can see here that I have 5 load combinations in total, a mix of ULS and SLS load combinations. And the help system will explain what type of load combinations we recommend for this composite steel design workflow. But effectively, what we have here is we have the first one, the ULS pre-composite, is a combination of the ULS factored dead weight of steel, which is the steel deck and the concrete, plus the factored self-weight of steel, and the factored construction live load. So you might remember here I had that slab load case, which was an external load case. Because I'm not modeling the slab explicitly, we're applying that as an area load. Next one down is the ULS post-composite, which has the ULS post-composite superimposed dead loads, plus the post-composite live load. I have below that the serviceability camber load combination, which is SLS unfactored self-weight of concrete, plus the steel deck, plus the self-weight of steel. I have my serviceability post-composite total, which is the SLS unfactored post-composite superimposed dead load, plus the unfactored post-composite live load. And then finally I have my serviceability net total no self-weight, which is the SLS unfactored self-weight of concrete, plus steel deck, plus the unfactored self-weight of steel. And you'll notice here that we have the word net in here. It wasn't a thoughtless inclusion. That is actually an important detail with this load combination. The word actually tells STL that it's going to be used for deflection checks and camber determination. And as I mentioned, there are more details on how these combinations can be set up in the help system. I'm going to go back to the geometry window, and the first thing we want to do is actually go to the settings menu, and under preferences we can just review a few details. I'm going to start with the design codes tab, and I can see here the design code that I'm using, in this case here the S1619 code. This also works with the American code and the Korean codes as well. I can switch to the Solver tab here, and I can see that I have this option that says this structure will be modeled and analyzed using a stage construction sequence. So I'm going to toggle this on. And in the one below that, I'm going to toggle on as well. It says the stage construction will be limited to analysis and design of composite floors. So I'll toggle this guy on, click OK. And on the surface, it doesn't really look like anything has changed. But we will notice here where I was looking at my structure folders that I had earlier introduced, we have this construction stages tab now. And I can see here when I click on construction stages, there are two stages. There's a pre-composite and the composite stage, and they are both identical at the moment. So what I'm going to do is I'm going to use this, and moving forward we'll be able to differentiate these according to our steel design workflow, our composite steel design workflow. So I'm going to start by just selecting this first stage, which is my pre-composite stage, and I'm going to run an analysis. So I'll click on the Analyze button, and I'm going to run a linear static analysis. I'll click OK. And I'll just drag this over to my other screen here from my main monitor, and you can see what is happening here when we run the analysis. It separates the analysis into two different stages. So I have my first stage of running a linear static analysis for all 6 load cases and 5 load combinations. And it does the same thing for stage 2. Now in this scenario, both stages are identical, so it's not going to give us any unique results from one stage to the other, but we're going to differentiate them in the future. So effectively I have 2 models being analyzed within the same TEL file. Now I've looked at, I've got my graphical results here. I'm not going to spend too much time on this. We can maybe just introduce here, for example, the bending moments. This is just looking at self-weight loads, so you can remind ourselves that some of these beams have continuous spans versus some of them are simple spans. But let's just jump into S-Steel. I'll click the Steel Design Model button. And this has brought us into the Steel Design interface. And I'm actually going to start in the Design Input window. So I'm going to click on this button here, and I'm in the Design Input window now. And I'm going to activate stage number 2, the composite stage. And what we want to do is we want to size our beams to meet our composite demands. And something that I also want to introduce at this stage here is our design model. So I can go to the View menu, and I can click on Design Model. We can see it with the option to display our group names. I'm going to toggle this on. And we can see here that we've got labels for each of our design groups. So I've actually set this up in advance, but basically what it's doing is it's grouping our members that are designed in a similar way together so that we can design them in a more efficient fashion. S-Steel allows us to control our design groups or not have any design groups at all, but what design groups do is it groups these members that have the same cross-section together, and it says for the design, whatever section will work for the worst performing member in this group is going to dictate the section choice for the entire group. So if you have one member that might be lighter utilized than its neighbor in the same group, the section that's going to work for that higher utilized section is going to be applied to all the members in that group. Now you have control however that's set up, but it does allow you to design perhaps in a more practical way rather than having every single member have a different cross section. Now I haven't actually set up every single design group yet. You'll notice here that I've got some for my joists, some for my depth restricted beams, my girders, and so on. I'm actually going to just modify this a little bit here, so I'll just unselect all, and I'm going to select just the edge beams here on the edge of my holes, and I'm going to remove them from this default group that has put them in, and I'm going to just actually use this define a subset for sections to study. Right click on this, and you can see here that it's set up this dialog that says my current S-frame section is a W530 by 219. I might want to consider other sections that could be, or section types, like maybe more than just a W610. I can toggle this on or off as I like. I can also set up my group name, and I'm just going to call this whole edge beam. And I can see here which sections are going to be considered for the design. If I can't access all of these on my site, I can exclude them. I can sort based off of different criteria. So I can set up my own custom criteria beyond just what the code requires me to do for this design. I'm going to click OK, and I'm going to create this design group, and you can see that's done here. I will also just introduce one more, so if I just unselect these guys here, and I'm just going to look at my depth restricted beams, which actually have the same cross-section currently as the choice design group, but I've separated them out for that purpose. So I just selected one, but I'll select the rest of the members in that same group by toggling this button here. And I can select all the members in that group, and I can see here, if I just look at the design of, or the subsets of sections for study, this is my design group that's been set up. Depth restricted beams. I'm looking at W460 by 10 sections. And let's just say for this particular example here, I want to set up my own limits for what can be considered. Right now we have 36 different sections in that list that we can consider, but I might decide here, you know what, I have some equipment that I need to maintain a proper height for, so I want to go a little bit more strict on my depth. So I'm going to reduce this depth limit here to be anything less than 420 millimeters. So this original list of 36 sections, when I filter that down to be less than 420 millimeters, now I only have 9 sections I can choose from. So I'll click OK, and now that list is a lot smaller than it was. And I'll click OK again, and we've set up some of our design groups a little bit more in a custom fashion, I suppose you could say. So I'll just select my whole structure once again, and I actually want to look at setting up a couple different design parameters. The first one being our deflection criteria. So I'm just going to click on this tool here, the deflection criteria. I'm actually going to right click on it, and it's going to open up this dialog. Here we can see all the different load cases and combinations that we have, and we have this toggle to allow us to decide whether we want to run a deflection check for that particular case or combination. So I'm going to check on a few of these, my live load, my cladding load, and then my SLS load combinations. And I can specify my L over limit. So for live load here, I'm going to say L over 360. For my cladding, it's going to be 750. And for cladding, I'm also going to set up my own absolute deflection of 15 millimeters as well. And this is going to serve as a basically capacity for the design checks that we're performing. An SLS capacities, I suppose. So if we exceed this deflection limit, we're going to have a failing code check. For my camber load combination, I'm going to leave that as 0. And then for the SLS post composite, that'll be 240. And for the net total no self weight, that's going to be 180. I'll click OK. And I've got that design data set up in my model now. The next thing I want to do is start initializing some of my composite data. So I'll go to the Edit menu. And you can see we have this option to initialize composite stage. I'm going to click on this. And it allows us to identify and set up some of different parameters that will help with the camber determination and composite properties. I'm going to start by toggling on the option at the top that says include slab overhang for effective width calculations. I do actually have my slab overhanging my beams and my girders in a few different locations, including around this hole as well, actually. And then we can set up things like our minimum camber. So I'm going to say my minimum camber here is going to be 20 millimeters. My maximum camber is 75 millimeters. My camber increment is 5 millimeters. I'm going to have a minimum length for the beam that I'm going to camber as 700 or 7,500 millimeters or 25 feet. And then the minimum depth of the section I'll consider cambering is 300 millimeters. And the maximum depth will be 900 millimeters. And lastly, we can include details about what's considered a long span. I'm going to say that's going to be 15 meters here. Now I also want to set up some composite properties here. So I'll click on the composite properties button. And with this, I'm going to go ahead and choose my deck slab system. So you can see all these different options that we have available to us. So here, if I look at, right now I have a 100 millimeter slab and I have no deck. Maybe I want to go with something a little different. Like I can see here's a 38 millimeter slab, deck, sorry, with a 65 millimeter slab. And you'll notice here that the stud length is calculated based off of these dimensions. If I switch to a thicker slab, it's going to adjust that stud length accordingly. So I'm going to go with a 50 millimeter deck and an 85 millimeter slab. I want to choose the concrete strength of 30 MPa. I'm going to use a normal density concrete. I'll say here that my ribs are perpendicular to the beam. And I can have up to 2 studs per rib. So I have n equals 2. That is up to 2 studs per rib if it's required. We have the option to place the studs on the center of our ribs if we want to. And we can control the stud distribution whether it's uniform or optimized. The optimized meaning that it will actually apportion those studs based off of where the shear demands are highest, rather than just uniformly throughout the entire pad, or beam rather. So you can see we've got quite a bit of control over the data that we can enter here. We can control the maximum percentage of full composite and the minimum. We can define our own stud length and ratios for the depth there as well. So I'm just going to click OK and accept these parameters, and I'll click OK once again. And you can see here it says any previously defined composite steel design data, including camber, will be reinitialized. Do you wish to proceed? I'm going to click yes. And what we notice here, if I maybe just switch out of my deflection criteria tool and I zoom in a little bit more, we can see that we have some effective lengths that are set up for our beams. So it's showing us here the type of deck system that we have, so 50 millimeter deck and 85 millimeter slab, and it's showing us the orientation of the effective widths on each one of these beams as well. And I could select one of them, just maybe I'll isolate this one here along the edge of my hole, and I'll click Edit, Composite Beams, and it can be brought back to that previous member here, or dialog rather, and I can see the length, or the width rather, of our slab on top of our composite beam. So it's showing me here on one side I have 900 millimeter effective width, and on the right side it's just 159 millimeters. We'd have a slight overhang considering that we're taking this from the actual center line or the neutral axis of that beam. So we would expect some asymmetry for this beam because it doesn't have any material or any slab on this side. Now if I look at another beam that's perhaps a little bit more symmetric, click on this one here, I can click Edit, Composite Beams again, and we'll notice here that we have equivalent left and right slab width. Now if we just back out of this view here and I select my entire structure once again, I'm actually going to switch to a different tool. I'm going to click on this Effective Length Factors tool, and I just want to identify here that S-Steel has automatically identified the fact that these beams are supported laterally on their tops, so the effective length factor has been adjusted as well as the unsupported length factors. You will notice as well for these girders that have multiple joists intersecting them that the effective length factors are representing that automatically. So that's something that you can adjust, but it will set that up for you automatically. Now to take a step back here, the general workflow, if we're to break it down into kind of the high level components for this composite steel design, is we want to first design our steel beams for the composite demands. Then we want to reanalyze our structure because our steel section sizes have changed, so we're going to get new forces, new masses, and so on. And we want to code check for the non-composite strength and camber requirements. Then we're going to initialize the camber for the SLS loading, and then code check our model with the camber for the post-construction loading. And if necessary, let's say we aren't failing some of our code, or we are failing some of our code checks, then we can always choose new sections. And of course, once we've done that and we've sized our sections and they're all passing according to the gravity loads that we've applied, we can then use that model as a starting point for applying our lateral loads and more. So I'm going to start here within the design input window. Like I mentioned, I'm in the composite stage and I'm going to size my sections for the post-composite strength requirements. So here I'm going to go to the Run menu and I go to the Design, and I'm going to select which load cases and combinations I want to consider for the design. So I'm going to consider my live load, my cladding load case, and then my load combinations 2 and 4, which are the ULS post-composite and the SLS post-composite loads. And I'll click OK. And S-Steel is running through the design of these members according to those design groups that we'd set up. And you can see here it's giving us utilization ratios and cross-section sizes. And this may just remind you of the different cross-section design groups that we set up, or member design groups rather. So we have our depth-restricted beams here, which are using a W410 section. Then we have next to that a bay that's using our standard joist cross-sections, which are W460. And you can see the utilizations in each. They're about utilization ratio or demand capacity ratio of 1. Some of them are different. Again, if they are part of the same design group as their neighbors, they will have perhaps over-designed design groups or utilizations if they are part of a group that is contained with a higher stress section. Now I'm going to return to S-frame with this model. I'll click the Build Analysis Model button. And it's going to ask me, do you want to update S-frame with the new proposed sections? I'm going to click yes. And it's not going to overwrite our sections or our model. It's going to ask us to save a new one. So I'll just rename this file here. And we're going to return to S-frame. And what I want to show you first of all here is in the pre-composite or the construction sequence window here, we can see that we have our section properties, and it's showing us the section properties for each one of these members. So this is using the sections that we've redesigned for. And these are the pre-composite stage, so these sections are not composite sections. But you'll notice here that we have equivalent sections here in this list that have the word composite after it. So we pretty much have a one-to-one or a one-to-many relationship between the sections in this start of the list where we have our non-composite sections and the bottom of the list where we have our composite sections. You will notice that some of them, like this W530 by 66, for example, have multiple composite sections because we might have a member that has a different effective width than the rest of the members in that design group, perhaps. Or maybe we have a different shear stud layout, and so it's going to have different section properties. I can actually right-click on the section properties tool, and I can see here, if I look at the W530 by 66 section, let's just use the moment of inertia that we see here, and compare that to a composite section property, and we can see that moment of inertia has jumped up. And that will be the case for any of these composite sections that we notice, the inclusion of that slab and the influence of that effective or the moments of inertia and so on our section properties. And if I switch between the pre and post composite stages, we're going to see here where each one of these sections is assigned in our model. So I want to reanalyze the model, and I'm going to do that here really quickly with a linear static analysis. And you can see here we're getting a clean solution again. Now we do have a bit of a divergence between our first stage and our second stage because of those composite section properties that we have. And let me just select one load case here as a comparison. I'm going to select the live load case, and I want to look at the deflection. I'm in the pre-composite stage right now, and so we can see there is some deflection in the model. And I'll just select this beam right here. This is one of my perimeter beams. And actually, I want to look at the deflections here. So let me look at the properties, drag this over, and I want to look at the Z deflection specifically. And I can see for the pre-composite stage, I'm getting 27.76 millimeters of displacement in the Z axis. If I switch now to the composite stage, and I look at the same section or the same member, here I can look at the deflections, and I can see that it's actually about half of the original deflection. So that is showing us that the composite action is reducing that deflection. Now I'm going to go back into S-Steel. Click the Build Steel Design Model button. And I'm going to activate stage 1 here. So this is my pre-composite stage. And we can do things like we can review our effective length factors. It's unlikely we're going to have to make any changes to this, but obviously we can if we want to. And I want to code check the structure for the construction load cases, or load combinations rather, for both strength and serviceability. And so this is going to evaluate the non-composite strength and camber requirements. Now their sections have been sized appropriately for the composite loading. So I'm just code checking here again for the pre-composite stage. I'll click the Run button here, and I'm going to code check this for load combinations 1 and 3, which are the ULS pre-composite and SLS pre-composite load combinations. And we can see here that we're getting utilizations all less than 1. Now, it's just worth noting here that I'm really only concerned with the design of the horizontal members in the composite floor system. I'm not so concerned about the braces or the columns, which we can design in another workflow. However, I'm going through that process to code check them here as well. It's also worth noting that I'm getting utilizations less than 1. You can see like 0.8, 0.5, 0.3 for my construction load combinations. If we were having members that were failing, we could always adjust that later on. I'm just going to look at one of these as an example here. I'll click on this one here, 0.8 millimeters or 0.8 utilization. And I can see here it's being checked against the pre-composite ULS load cases or combinations and the SLS load combination. And I can see here the strength checks that it's performing with the clause references as well. I can see that there's a deflection check that's been performed. And we don't have any camber considered yet, but I'm getting a deflection of 37.693 millimeters. So I'm just going to write this down, 37.693 millimeters. And this is for member number 52, which is a W460 by 60 section. So I'm going to, now that I've code-checked this, I'm going to go ahead and activate stage number 2, my composite case or stage, and I'm going to go to code input window, and I'm going to initialize my composite stage for camber. So I'm going to go to edit menu, and I'm going to say initialize composite stage. And you might remember we had all this data here that we used to input or initialize our minimum and maximum camber requirements or limits, our increments, and so on. I don't need to change any of that. It's all been entered already. So I can just click the OK button. And this is going to initialize our camber. And as I mentioned in the past, it looks at our deflections from the SLS load combinations and uses that to determine how much camber is going to be required. So as an example, if we looked at a beam that had 1.5 inches of deflection in a load combination, an SLS load combination, we'd need at least 1.5 inches of camber. So I'm going to click yes to apply this information. And now what I want to do is, from the code input window here, I'm with the composite stage. I want to code check the structure for the post-composite, the post-construction load combinations. So those are the ones that we originally designed for. Make sure that everything is still going well according to the fact that we have camber in our model now. So that's going to be load cases 4, 6, load combinations 2, 4, and 5. And I'm going to click OK. And it's going through the code checking process for these load cases and combinations. And we can see once again, here we're getting utilizations that are less than 1. Now we can change the threshold for what is considered an acceptable utilization, because having a utilization of 1 may be a little too close to comfort for some. We haven't really gone into that yet here, but what I do want to introduce is just some utilizations and some of the checks that are being performed. So here I'm in the code results for my composite stage that we checked according to the construction or post-construction load cases and combinations. I can go to code details, and you can see here we have our live load case which is undergoing bending for this particular check. And we can see here we're looking at things like the shrinkage deflection for a pin end condition with ribs perpendicular to 2 studs off center, and we can see the clause associated with this. We can also see the composite beam moment resistance with a 30 MPa slab on top with 2,300 kilograms per meter cubed concrete, how many studs we have, and we'll look at this more, how we can display it graphically later on, as well as the effective width, and all the clause references associated with this. Continuing down the list here, we can see the deflection check that's being performed with a maximum deflection of 33 millimeters that we have, and this is pretty close to failing our code check, but not quite. So the live load case is governed by deflection. We can see here we also have, well, this model we have cladding, but not in this particular beam, so it's not loaded for that load case. And continuing down the list, I just want to actually move to the SLS load combination here. And I can see the max deflection that we have, as well as this residual camber. And I just want to introduce the fact that when we have residual camber, in this case here is 2.693 millimeters. We might want to know where that number has come from. So that 2.693 millimeters here is basically, well, it's the residual camber is the deflection from the weight of the wet weight of concrete and the self weight of steel minus the camber that's already been applied. And it's something that we haven't really looked at graphically, so I just want to explain where that data is coming from, because right now I've just been looking at utilization ratios. But if I go to the view menu, I have different ways of displaying this information. So I can see here color coding, I can see color coding plus utilization ratios, governing members, and then section plus total studs and camber. So this is showing me here that for this beam that I selected, It's a W460 by 60 section, 34 studs along its length, and 35 millimeter camber. And I can see the different amounts of stud required for different members. And I also have this detailed studs and camber display. And when I use this one, and we look at the results here, we can see here, it's displaying it a little bit differently. So this is showing me here I have 34 at 1 per rib. There might be scenarios where I have more than 1 stud per rib, and that will be displayed here as well. What we'll also notice is for some of our continuous beams, which have girders joists intersecting them, we have the cross-section size and then the total number of studs. And it's actually broken the stud layout into each span. So I have, in this case here, a different number of studs in different spans. And you can see it will actually vary depending on which particular beam we're looking at. So I have this information all displayed nicely graphically for me. I can also look at the file menu and I can produce a design report for the entire structure as well. So I can click on print key results and I can control which data is in here and which data I might want to display. I'm going to actually just exclude some of this data just for the sake of brevity. Click OK. And we're getting a nice table of all the performance of our different members. And at the bottom we'll also get a nice list of quantities as well. So this is showing me basically all the different steel sections in my model, the length of material that's being used, the weight, the surface area, and I don't have cost data for this particular application, but we could have also entered that as well. And once we're done with this, we can go back into S-Frame rather, update our models if we need to. And at this point, we might want to consider looking at the design of the rest of our structure and looking at the effects of lateral loading and so on. And I can do that by just simply converting my model to a non-stage construction model. So I'll go to Settings again, Preferences, and under the Solver tab, I can untoggle the stage construction approach options, click OK, and when I do this, it's going to ask me, do I want to assign the composite stage to my structure or the non-composite stage? So I'm going to click yes, I want this to be my composite stage. And now the model has been updated and all of the design sections reflect the fact that we have the inclusion of that slab and deck system on top of our steel sections. And so now we can go ahead and run the analysis, further analysis rather, for things like lateral forces and so on. So that brings us to the end of this workflow introduction. There is plenty more to discuss on composite steel design, but I think now is a good time to stop for questions. We'll do our best to answer as many questions as we have time for. So I'm just going to mute my line here while we read the questions.